Good evening. This is the 46th lecture of the lecture series AS and A-level chemistry. We have been talking about the practical skill. In AS level, there is a chapter. Also in A level, there is another chapter, practical skill 2. And also analytical chemistry. So in AS and A-level exam, in both exam, students are supposed to give practical examination in AS level and A level. Well, in AS level syllabus for lecture 33 and 34, we discussed a lot about chemical analysis and what we need, why we do chemical analysis, why we need it. This sort of discussion we did in lecture 33 and lecture 34. And more specifically, in AS level course, there are discussion about mass spectrophotometry, UV visible IR spectrometry, acid-base equilibria, qualitative and quantitative analysis. These are very essential for learning chemistry, very, very essential for learning chemistry. We will see, and we will, of course, you already have seen in O-level chemistry and also AS and A-level chemistry. You have to go for practical classes and do what you read in theory, practical problem, solve it. And we also need some instrumental techniques to analyze it. Not only instrumental technique, but we also do some qualitative analysis, but just by using test tube and some very simple instrument, very, very simple instrument. But nowadays, to learn chemistry, we do have to go for analytical techniques. There are lots of different techniques. But in AS and A level, we have to study mass spectrometry, UV visible IR spectrometry, acid-base equilibria, etc. And in A level, analytical chemistry, gas chromatography, and nuclear magnetic resonance spectroscopic techniques. These are in the analytical chemistry chapter of A level syllabus. So we will be concentrated ourselves in gas chromatography and NMR spectroscopy technique, what we study. Probably next 2 lectures we will do that, and then that will end the lecture series of AS and A-level chemistry. Anyway, in the last lecture, I'll talk a little bit more about it. But now we go for basics of chromatography. What is it? You see, in laboratory and even in research laboratory, practical laboratory, they do have some, I would say, schematic. This is schematic paper chromatography. Then what is paper chromatography? That is used to separate mixture of compounds. And to that, we need to have a solvent, which we call mobile phase. And then we have to have a stationary phase. Let's go to this schematic diagram and see what it is. Well, we have a glass tank. There's a glass tank, and that is a paper clip, and we take a paper in it, and then we have solvent. That is solvent, and do remember that when we do paper chromatography, we must have to have a reference compound, pure reference compound. Otherwise, we cannot solve the problems. So this is a pure reference compounds. These are pure reference compound, and this is the sample to be analyzed. So what happened after we start the experiment? We will see that the chromatogram is like this. that we separate the samples solute, and that's what we call in the different time, and we call it retention time. We will talk about it in the next slides, but then we say mobile phase and stationary phase. That two are very necessary for doing paper chromatography. Solvent is the mobile phase, and then the absorbent paper, this is a stationary phase. So the substance in the mixture, what will have then? Different affinities for the solvent and for the water. So they move at different rates, and we will find out that rate and then conclude what is in our mixture. Well, when we go here, we will have when we're doing paper chromatography, we use a factor, we call it RF values. RF values. What is RF values? Are recorded distance moved by chemicals in a mixture. So that's the mixture, and chemical in a mixture, the distance moving, that's what we have to see relative to the distance moved by the solvent. So we can get to this one and see what is RF value. We'll see that this is our compound, which we started there, and then we get this is a movement of the compound, and this X value, what we call distance moved by the chemicals. This is the distance moved by the chemical, and what sort of ratio we do that? The distance moved by the chemical and distance moved by the solvent. But this is the solvent. If we go back to our first picture, there is the solvent. Then solvent also moves, and as well as the compound also. So we take the ratio of this distance moved by the chemicals and distance moved from the solvent front. This is solvent front, so that's the distance, and the chemical which moved is the distance. We take the ratio of these two, and that's what we call RF value. So we have the RF values, and it's possible to identify the different separated spots on the chromatograph. We have to note that condition of experiment must be same. For example, we are putting a sample in a paper chromatograph, and then it is in a different temperature. We're putting a sample in different temperature or different solvent. It cannot be done by this. We have to have RF value which coated, and we should remember that we have to have same temperature and same solvent to do this. In paper chromatograph, we get also colored substance can be seen directly on the paper. But others are not seen directly. We have to spray it with some chemical that forms colored compounds on the chromatograph. For example, we take amino acids, and when we spray ninhydrin spray, we will see a bluish spot for the amino acids. So another technique we have to remember, that partition coefficients of coefficient. The principle of partition of coefficient solute between two solvents, we use that, and then a mixture are separated in chromatography. That is, in chromatography, partition coefficients of the components in a mixture corresponds to the relative solubilities in two solvents. Okay. Now, partition coefficient chromatography, what is this? The mobile phase is in the solvent chosen. The other solvent in the water trapped in the paper structure, which is a stationary phase. That's what we show here. You see that the solute molecules dissolved in the stationary liquid phase. This is the liquid phase. Stationary liquid is this one, and then a solid supported with partition paper chromatography. The mobile phase solvent moves on the stationary liquid phase, water trapped between the fiber of the paper fibers. Okay, this is what we need for partition coefficients in chromatography. Thin layer chromatography is another technique of chromatography. In this, the stationary phase is a solid one, thin layer of solid. And what sort of solid? Either we take silica or alumina. And that is, the silica or alumina is supported by on a glass or a plastic plate. The rate at which the sample moves up at the TLC plate also depends on the equilibrium between absorption on the solid and solution of the solid. Position of equilibrium varies from one compound to another, so the components mixture can be separated. One very good advantage for thin layer chromatography, it's a very quick, cheap, and it needs very little sample for analysis. Amino acid in peptides or proteins can also be investigated by this thin layer chromatography. Okay. Then we have another type of chromatography. We call it gas liquid chromatography, that is GLC. Well, you see, the sample should be in the form of a paper. It could be gas, it could be volatile liquid, it could be solids, but when we inject it, it should be in a form of paper. So there is a sketch of gas liquid chromatography. What you do, this is injector port. This is injector port. Sample injected through a silicone rubber septum, and mobile gas, the carrier gas phase is mobile phase introduced here, and then it's an injector oven to make the sample in vapor form, and then this is a column. It's a column, and this is column oven because it's a gas. So column is usually 1 to 5 meter long and 3 to 6 millimeter in diameter. And then we have exit, and we record the computer, recorded in computer and detector. And this is detector oven, this one, detector oven. So then what we say that we can introduce a sample like gases, volatile liquids or solids, and then it transform into vapor, and the component of a gas liquid apparatus. So I talked about it. The stationary phase is a non-volatile liquid, which has a high boiling point. What those liquid are? Long chain non-polar hydrocarbon, and converted into a solid support, so called it. So I already talked about it, silica tightly column into it. And then the mobile phase is an inert, unreactive gas, which is called carrier gas. And this is sometimes as helium or nitrogen. The helium is costly, therefore, in many cases, we use nitrogen. The tiny solids, particles in the column, have very large surface area over, and the partitioning can occur, resulting in the excellent separation. Here we see a gas chromatogram from a mixture of volatile organic compounds. You can see this is, if you inject here, this is the time in minutes, 0 time, and then we see how ethanol and ethoxy, ethane, propane, hexane, 1, heptane, and pentane, 2 on 1, 2 on. This is separate. This is what we call retention time. So the detector at the end of the column records the retention times and how long it takes each component to pass through the column. That's what we record, and then find out the compound that we have in the mixture, what we want to analyze. Well, we can also use GCL, gas liquid chromatography, in quantitatively determining the percentage of mixture of the compounds in a sample. Okay, so component peaks first, we have to identify the component peak and then measure the area we found for the component peak. The peak is roughly triangular in shape. So area is approximately half base into height. So we use this and then we can find if there are, let's say, if there are esters of 3 esters A, B, C, what we can do, we can find the peak area or height of A, and then sum of the areas of heights of A, B, and C. And that gives you the percentage of A quantitatively in gas chromatography. Well, this is used to test steroids. Something. We can also use Formula One fuel for motor racing. We use it in medical diagnosis for blood sample. For example, we measure, we get the percentage of oxygen, nitrogen, carbon dioxide, carbon monoxide in blood sample, and we need only about 1 millimeter cube or 1 centimeter cube sample. GCL is often combined with mass spectrometry to separate and rapidly identify the component mixture. We go for that. Okay, we have another chromatography, which we call high performance liquid chromatography. This is a sophisticated version of column chromatography that we have discussed. Well, here is a picture of a researcher analyzing a sample using a HPLC. Well, here in this case, the packing materials are packed in a steely column, and type of column is, let's say, about 10 to 30 centimeter long, and internal diameter is about 4 millimeter. The use of these particles, packed particles, increases the surface area, as I say, of the stationary phase. This makes separation efficient, but it means that a high pressure pump is needed to force the solvent through the tightly packed column. This is why sometimes it is called high pressure liquid chromatograph. Okay, an advantage of high pressure liquid chromatograph or HPLC is that the experiment is done at room temperature. So for biological sample, it is very good technique for to see the to do the experiments with HPLC, because at high temperature biological sample decomposes, and therefore we cannot do gas chromatography in high temperature. So HPLC advantage is this, that we can use this for separating biological molecules such as protein, etc., or even urine and blood sample to investigate what happens when a drug being administered to a body and how they are metabolized. That's what we can see from this. Well, another one, gas chromatography, is that the gas chromatography mass spectrometry. Gas chromatography coupled with the mass spectrometer. We discussed mass spectrometer about the mass spectrometry, the theory, and we have seen lots of mass spectrogram in AS level practical or practical skill 1. And now what we are doing, we are using this gas chromatograph and coupled with the mass spectrometry, which is a very powerful technique to separating, identifying, and measuring complex mixture of chemicals, widely used in drug detection, forensic investigation, environmental monitoring, and even in airports security, they use it. Even in space, they take a tiny GCMS for analyzing samples collected in space or on the surface of planets. this is how a schematic diagram showing the key feature of gas chromatograph, mass spectrometry, gas chromatography mass spectrometry system. Here is a cylinder which is a regulator, this strap, and then auto sampler here, inlet, and then we see already the column. It transferred to a mass spectrophotometer, that is a MS detector, and from detector it is computerized, and we can get a sample like this, a gas chromatograph, like this, and then we can. This is what is the number, which 1 to 400 in the time axis indicate the points at which mass spectra are recorded and stored. And this underneath, it is the retention time. Let us then take another mass spectra, GC MS printout, and what we have done here, we took from this spectrum that 91 in the mass spectra and analyzed it with the mass spectrometer, and then we have library, compound library, automated library, and from there the mass spectra can, you know that every compound has got a unique mass spectra, and therefore we can find this from the library and find the mass spectra of the, let's say this one, chromatograph, GCMS printout, which shows methyl benzene, and then 1,3 and 1,4 dimethyl benzene peak, and then ethyl benzene peak, and 1,2 dimethyl benzene peak. And that is what you can see, and we can see that this is a very essential instrument to analyze organic molecules, specifically organic molecules, and even unknown molecules, to characterize the unknown molecules with the help of GCMS. I have to say a little bit about few limitations of GC, and that limitation is overcome with if we have a GC with mass spectra. What is the limitation? Similar retention time in GC, which means that we cannot identify the chromatograph with chromatograph alone. And if the conditions are carefully new chemicals we cannot identify because we don't have a reference standard for that. So this problem can be overcome using this GCMS technique. Then we go for, up to that we have been discussing about different types of chromatograph, and also we saw some of the chromatogram and how we can interpret it. That's what we have discussed. And in the next lecture, we will take nuclear magnetic resonance spectroscopy. And here we have to say one thing, that A-level chemist student need not to know the in-depth theory of NMR, but they are supposed to interpret the NMR spectra and structure molecule. That's what they are expected to get in the exam and practical skill exam. Well, thank you very much for today, and we will meet in the next lecture and see more about nuclear magnetic resonance spectroscopy, and which will I hope that by this lecture, nuclear magnetic resonance spectroscopy, and we will finish the AS and A-level chemistry lecture series. For the next lecture, please, till then, we say goodbye today. Thank you very much.